Okay, today we're doing experiment number 10. This is torques, equilibrium, and center of gravity. Okay, so what we're going to be doing is going to be hanging weights on a meter stick that's on this balance. Okay, we're going to try to balance it out. So the conditions for equilibrium, translational equilibrium, is the sum of the forces equals 0. Right? That keeps it from moving up and down or side to side. Well, that's taken care of with this blue stand here, so this prevents it from falling to the floor. So that satisfies the translational equilibrium. What we're looking at here is going to be the rotational equilibrium, where the sum of the torques equals 0. So in particular, we want the counterclockwise torques equal the clockwise torques. So any weights hung on the right side will produce a clockwise torque. Any weights hung on the left side will produce a counterclockwise torque. And the torque, of course, is the force, which is the weight, times the moment arm, which is the distance from where the weight is hung to the fulcrum, or the balance point. So if I have M1 on this side, M2 over here, this torque is M1 GR, and this one is M2 GR2. So this is a clockwise torque, this is a counterclockwise torque. Notice we have the same G on both sides, so we don't actually have to multiply by G because the G's will cancel out. So we're just going to be looking at the mass times the moment arm. So mass times moment arm on the left side equals mass times moment arm on the right side. The R's are the actual moment arm. You'll notice in the laboratory report we have both R's and X's. The R's are the actual moment arm, the distance from the weight out from the balance point, or the X is actually the number on the meter stick, the position on the meter stick of the X's. So a particular moment arm, R sub I, is equal to the absolute value of X sub I minus X sub 0. X sub 0 is the balance point on the stick. Okay. So again, the X's are the numbers on the stick. The R's are the difference between the number on the stick and the balance point, and that will give you the moment arm. So that's what we're going to use in the calculation. So I'm going to make the measurements. You will have to do all of the calculations. All right, so you'll have to find the R's. I'll give you all the X values. Okay? And don't forget to put units. Now, units of torque, of course, are force times distance, but we're just doing mass times distance. So we're going to use grams centimeter for our torque units. That's not a true torque unit, but it will suffice for the purposes of this lab. Also, it asks you to draw sketches of the arrangement. So we just follow the step-by-step procedure in the experiment document, which I'm going to go through here. And then I want you to actually draw the sketches in the lab report as well. Okay? So that's how we're going to proceed with this. Okay, so looking at the procedure, step 1, we want to find the mass of our meter stick. So I have a laboratory balance here, and I have to check 0. So you can see it's not quite zeroed, so I need to adjust that. And make sure it's zeroed first. Okay. Now it's zeroed. I can put my meter stick on the left side and measure the mass of the meter stick. That looks about balanced there. So I read that. I've got 64.50. So the mass of the meter stick is 64.50 grams. Okay. Check again. Yeah, that's what I got. 64.50 grams. Okay. That. Now I want to put in the clamp, and I'm hoping I'm lucky. Not all these meter sticks are completely uniform, so I'm going to put it on the 50 centimeter mark, and it balances. So my X naught is 50 centimeters, so 50.0 centimeters. Okay, we're only going to go to 1/10 of a centimeter. Okay, so 52.0 centimeters. It balances right in the middle. That's pretty lucky. Most meter sticks are not that uniform. Okay, so then we go to step 3, which is case 1, 2 known masses. So with the meter stick on the support, we're going to suspend a mass of 100 grams at the 15 centimeter position. 15 centimeter position is over here. So I have some little strings, and I have a 100 gram mass. So we're going to use a little bit of tape to hold the things together. I'm going to put a bit of tape here. Keep this from falling off. And then put this at 15 centimeters. Okay? And then I want to put a 200 gram mass. So I've got 200 grams here. Little piece of tape. And put that on the other side until it balances. Not quite. Oops, this slipped. 15. Put a little piece of tape here so I can hold this at 15. Pretty close. Okay, so this is about $67.5. 67.5. Okay, so my X1 is 15 centimeters. That's already given, and this is 67.5. Okay, my M1 is 100 grams. M2 is 200 grams. Okay, so that completes case 1. You'll have to calculate the moment arm and then the clockwise torque and counterclockwise torque. And then you find the percent difference between the clockwise and counterclockwise torques. Okay, so that's case 1, part A. And part B and part C is doing the computations. Okay, next is case 2. That goes here. 3 known masses. So with a meter stick on the support stand at X naught, suspend a mass M1 of 100 grams at the 30 centimeter position. So I'm going to move this to the 30 centimeter position. And secure it with a piece of tape at 30 centimeters. And then we want M2 is 200 grams at the 70 centimeter position. So I'm going to put this at 70 centimeters. Another piece of tape. So M2 is 200 grams at 70 centimeters, and now I'm going to spend 50 grams, M3 at 50 grams, and adjust the moment arm until the system is balanced. So this side is too heavy, so I have to put my 50 grams somewhere on this side. So I've got 50 grams. And I'm going to suspend this one somewhere here until it balances. And that looks like it's right at 10 centimeters. So my M1 was 100 grams. M2 was 200 grams. And M3 is 50 grams. And it's going to be at 10 centimeters. So the M1 of 100 grams at 30 centimeters. M2 is 200 grams at 70 centimeters, and I find my M3 at 10 centimeters makes the thing balance. Okay, so that's case 2A. Case 2B. Calculate theoretically the moment arm R3 for a mass of 50 grams for the system to be in equilibrium if M1 100 grams at 20 centimeters and M2 equal 200 grams at 60 centimeters. Check your results experimentally and compare with the theoretical value using your percent error with the theoretical value taken as the accepted value. Okay, so I'm going to pause the camera and do that calculation. Okay, for case 2B, I found that we have to put our M3 of 50 grams at 70 centimeters. All right, so I'll give you that value, 70 centimeters. Okay, next is case 3. We're going to use an unknown mass. So with the meter stick in the support stand, suspend the unknown mass at the 10 centimeter position. All right, so I'm going to take these off. Here's my unknown mass, and we're going to put that at the 10 centimeter position. So I'm going to tie that one, tape that one at the 10 centimeter position. Okay. Now from the other side, we're going to put M2 as 200 grams and adjust it until we have equilibrium. So here's my 200, and adjust it till we have equilibrium. Oh, pretty close to 90 here. That's it, 90 centimeters. Maybe 91. X1 is too far. 90. So 90 centimeters. Okay, so my case 3, I adjust the position till equilibrium is reached. So my M2 is 200 grams. And its position was 90 centimeters. My X1 was at 10 centimeters. Okay, so then you'll have to calculate the R's and calculate what the value of this mass is by balancing the torques. Okay, so I'm not going to do that calculation. You'll have to do that. Then we want to remove the unknown mass and measure it on the laboratory balance. So I'll go ahead and do that. And I'll remove that. I'll even leave the extra tape. And we'll get the laboratory balance out. So it's looks about it. Is that it? Not quite. That's it there. Okay, wow, right on the tick mark. So I got 200.50 200.50 for my measured gram. 200.50 grams for my measured value for my unknown. Okay? So that completes case 3. Okay. So next, we have case 4. So case 4, we're going to do the meter stick with one mass. All right? So I'm going to give pause on the video here for a moment. Okay, so for case 4, we suspend 100 grams from the end of the stick here, and then we move the clamp until we have it balanced. Okay? And when I do that, that's pretty close. Okay, that's about right there. Okay, and I've got 19.6 centimeters. So 19.6 centimeters is the new equilibrium position. That's my new X0. Okay, so that's the point where it balances. Now what we're going to do is, for case 4A and 4B, we're going to assume that the mass of the meter stick acts at the center of mass, which is about 50 centimeters. And we found that the mass of the stick was 64.5 grams. So in the case 4A, M1 is 100 grams at 0 centimeters. The mass of the stick is the M2, which is 64.5 grams, and that acts at the 50 centimeter position here. Okay, so that's my X2. My X0 prime was 19.6 centimeters. Okay, from using those mass values, compute the moment arms and compute the counterclockwise and clockwise torques and the percent difference. Okay, now for case 4B, we're going to treat the meter stick as if it were two pieces. We have one piece on this side and another piece on this side. We need to find the mass of this side and the mass of that side. All right, so we take the total mass divided by 100 centimeters, and that gives us the number of grams per centimeter. And then if I multiply the number of grams per centimeter times this many centimeters, that will give me the mass on this side, which is M3, and the number of grams per centimeters times this many centimeters will give me the mass on this side. Okay? So we had 64.5 grams divided by 100 centimeters gives me a mass per unit length of 0.645 grams per centimeter. So 0.64 grams per centimeter times this length, which is 19.6. So I have 0.645 times 19.6 centimeters gives me 12.6 grams. So my M3 in case 4B is 12.6 grams. Okay? Then I take on the other side, so I take 100 minus 19.6. That gives me 80.4 centimeters. So the length of that side is 80.4 centimeters times 0.645 grams per centimeter gives me 51.9. So M2 is 51.9 grams. Okay, so 51.9 grams for M2 and 12.6 grams for M3. Okay, so now my X3 is going to be halfway between 0 and 19.6. So I take 19.6 divided by 2, and I get 9.8. So my X3 is 9.8 centimeters. Now on this side I had 80.4, so 80.4 divided by 2 equals 40.2. So 40.2 centimeters is in the middle here, and I add that to my 19.6, so I get 59.8. So 59.8 should be my X3. So I put X2, 59.8 centimeters is my X2. Okay, so I want X2 to be halfway between here and here. Right? On this side I had 80.4, so 40.2 added on to the 19.6. So again, 40.2 plus 19.6 gives me 59.8. So 59.8, which is about here, just before the 60 centimeter mark, gives me my X2. Okay, so X2 is where the 51.9 grams, the mass of this side of the meter stick, acts. And the 9.8 centimeters about here is where the 12.6 grams, this mass of the meter stick, acts. Okay, so you can compute the torques using those values. All right, so next we'll go to 5A. Okay, now we're going to be doing 5A. It's called center of gravity. Okay, so we're going to have mass M1, 100 grams, suspended off the end of the stick, like we do here. Then I'm going to take another 100 grams and suspend this at the 60 centimeter position. So I put this out at 60 centimeters. And then I'm going to adjust my clamp until we're balanced. here. And that looks like I hit it right there. Okay, so we find that new position. Not quite. Okay, that's at 34.5, 6, 7, 8. 34.8. So 34.8 centimeters is my new x naught prime. Okay, so my M1 is 100 grams at the 0 centimeters. M2 is 100 grams at the 60 centimeters. So M1, 100 grams at 0, M2, 100 grams at 60 centimeters, and my new x prime is 34.8 centimeters. Okay? Maybe not. $34.9. Yes, 34.9. Okay? Now we're going to move this out to 70 centimeters and repeat that. So put the 100 grams out at 70 centimeters. So now my x2 is 70 centimeters. Find the new x naught. Just clamp a little bit. About there. Okay, that gives me 38.6 centimeters. So 38.6 centimeters. Now I move this out to 80. So I have 100 grams at 80 centimeters. And again, adjust this until it's balanced. Okay, and now at 42.5 centimeters. Then I move this out to 90. Right. Almost. All right, that's it. And I've got 46.3. 46.3. Okay, so at 90 centimeters. Okay, now that was supposed to be a predicted value, but that was actually what I measured, okay? So I will give you, that's the end now. I will give you these. So the measured value goes out here. You will write your predicted value in here, and that's the measured value. Okay, so you will have to do all the calculations. I give you all the measured values here, which I just measured, and then you complete the calculations. Don't forget to draw your sketches, just very similar to what's given in the drawing here. Just draw simple sketches for all the different cases, okay? And again, don't forget to put the units. Now our units are going to be grams centimeters. Those are not true torque units, but they will suffice for this exercise. So your moment arms again are the difference between the two X positions in centimeters, and your torques will be in gram centimeters. So you have to do the calculations and answer the questions at the end of the lab report. Okay? And then that will be it for this one. Okay, one other thing I wanted to point out to you, in case 5D, when you're calculating your predicted value for the x naught prime, the balance point, don't forget to take into account the mass of the meter stick, which acts at the 50 centimeter position. The mass of the meter stick was 64.5 grams, and that acts at the 50 centimeter position. So when you're calculating your balance point, you want to make sure you include that in your calculations. That's also pointed out in the procedure in step 7, case 5D. That's pointed out here. So don't forget that part in your calculation. And that'll make your numbers come out much closer if you do that. Okay? All right, so that's it.